Kurinji Senior Secondary School, CBSE, Namakkal.
Successful result producing school in state every year.
Administered by the Board of Directors with over 35 years of experience in the teaching field.
Special attention on art, craft, music, dance, silambam, yoga, skating and karate.
Focus on Hindi Sabha and Spell Bee Olympiad exams.
Smart class for effective and innovative learning and well-furnished library.
Solitary importance on sports and games in state and national level.
WhatsApp facilities to know activities of students and school inside the campus.
NEET, JEE, IIT coaching experts from Rajasthan and Andhra Pradesh along with our effective teachers.
Admission registration for classes LKG to +2.
Kurinji Educational Institution, Kavetipatti, Namakkal. Admission in progress. CBSE, KG to 12, contact 9025895176. Metric 6 to 12, contact 9344567484. For online admission, log on to www.kurinjischoolnkl.in.
In continuation to the last class, in this class we start with the 23rd problem. So up to 22 we have discussed in our till our previous classes. Right now 23rd problem from this chapter, dual nature of light, numericals. See here, a source S1 is producing 10 to the power of 15 photons per second of wavelength 5000 angstrom unit, full stop. Another source S2 is producing 1.02 into 10 to the power of 15 photons per second of wavelength 5100 angstrom unit, full stop. Then power of S2 to the power of S1. So he is asking ratio. This is what ratio of power of S2 to the power of S1 is equal to, right? So to get the ratio of power of S2 to the power of S1, first we have to go for calculation of power S2, that is what we are assuming here as P2, right? Then power of S1 as P1, right? So first we have to calculate P1 and P2, then you can get the ratio mathematically, right? Okay. So I will repeat once again the problem. A source S1 is producing 10 to the power of 15 photons per second, right? You know that according to Einstein, regarding the photoelectric effect, so light is, that is what light is, the combination of light consists of photons, right? So photon is like a small energy pocket, right? So 10 to the power of 15 photons per second of wavelength, 5000 angstrom unit, 5000 angstrom unit, okay, right, full stop. Another source S2 is producing, S2 is producing 1.02 into 10 to the power of 15 photons per second. So keep in mind, here we have two different sources. In source 1, 10 to the power of 15 photons per second of wavelength 5000 angstrom unit, and for another source, that is what different from S1, producing 1.02 into 10 to the power of 15 photons per second of wavelength 5100 angstrom unit, okay, right? And asking to find ratio of their powers, right? So power of S2 to the power of S1 is equal to, okay, right? See here, for source S1, see here, wavelength lambda 1 is equal to 5000 angstrom unit. For source S1, according to the given information, for source S1, wavelength lambda 1 is equal to 5000 angstrom unit, comma, number of photons emitted per second, N1 is equal to 10 to the power of 15, see here, 10 to the power of 15 is the N1 value. Now energy of each photon, you know that formula, E is equal to h nu, but there are but here we have two different sources, no, that's why first energy of each photon E1 to identify and to distinguish, one is S1, another one is S2. So when it is S1, you know, lambda 1 and N1 and E1, so all are see, we are that is what we are representing in terms of 1, you know, for source S1 lambda 1 wavelength and N1 is the number of photons emitted per second and E1 is the energy of each photon, right, regarding the first source, right. Okay, for source S1 is equal to hc by lambda 1. You know, h is the Planck's constant and c is the speed of light. These two are constant values. These two are constant values. That's why no need to write h1 c1. So simple hc by lambda 1. Next, power of source S1 is equal to, that is what power of source S1. We are assuming that as a P1. P1 is equal to E1 into N1. E1 into N1, that is equal to N1 hc by lambda 1, right. N1 hc by lambda 1. And for a source S2, same process. So whatever we did, the same thing we are going to follow. You know, here wavelength lambda 2 is equal to 5100 angstrom unit, number of photons emitted per second. N2 is equal to 1.02 into 10 to the power of 15. 1.02 into 10 to the power of 15. Okay. And energy of each photon E2 is equal to hc by lambda 2. Energy of each photon E2 is equal to hc by lambda 2. And then power of source 2, that is what P2 is equal to, power of source 2 P2 is equal to, right, E2 into N2, E2 into N2, that is equal to hc into N2 by lambda 2, hc into N2 by lambda 2. This is what power of source P2, power of source P2. Okay. And according to the question, he is asking the ratio of power of source 2 to the power of source 1, right. Observe carefully, he is not asking power of source 1 to the power of source 2, right. He is asking ratio of power of source 2 to the power of source 1. So P2 by P1 is equal to, you just write down these values. hc P2 means what, hc N2 by lambda 2 and divided by P1, that is what N1 hc by lambda 1. When it comes to the numerator, you know, it will be reversed, no, see here. So this is what lambda 1 by hc N1. hc will get cancelled, then finally N2 into lambda 1 divided by N1 into lambda 2. N2 into lambda 1 divided by N1 into lambda 2. Okay. This is what ratio of power of S2 to the power of S1. Okay. Next, see here. We are going to substitute the values. So what they have given, you know, it is what N1, 10 to the power of 15. And you know, this is what N2, 1.02 into 10 to the power of 15 photons per second, into, you know, what is lambda 1? 5000 angstrom unit. And what is lambda 2? 5100, that's all. 5100 angstrom unit. Okay, right. And you know, 10 to the power of 15 will get cancelled, and it is what, like you know, it is 1.02 into 5000. Here it is 5100. Okay. And if you do this process mathematically, you will get it as 51 here in the numerator and 51 here in the denominator. 51 by 51 means it will give us 1, right. So almost approximately this is 51 and this is also 51. Then finally we will get it as 1. That is what ratio of power of source 2 to the power of source 1, that is P2 by P1 is equal to 1. Right. Next question. See here. The potential difference, next question, that is what 24th question. The potential difference that must be applied to stop the fastest photoelectrons emitted by a nickel surface having work function 5.01 electron volt when ultraviolet light of 200 nanometer falls on it. Falls on it must be. So, if you see this problem, this from here to here, instead of asking, you find stopping potential. Instead of asking to find stopping potential, he has given like a definition. That is what see here. The potential difference that must be applied to stop the fastest photoelectrons. The potential difference that must be applied to stop the fastest photoelectrons emitted by a nickel surface, right? That is what stopping potential having work function. So, this nickel surface having work function of 5.01 electron volt. When ultraviolet light of 200 nanometers falls on it must be, okay, right. See here, solution. Here, incident wavelength lambda is equal to 200 nanometers. Incident wavelength lambda is equal to 200 nanometers, right. Work function phi naught is equal to 5.01. Phi naught is equal to 5.01 electron volt, okay. Here, this is what incident wavelength given and this is what work function given. Now, according to Einstein's photoelectric equation, I can write this value. That is what, I can write this relation. EVS is equal to h nu minus phi naught. H nu minus phi naught, that is equal to hc by lambda. In place of nu, we can write c by lambda. Hc by lambda minus phi naught, okay, where Vs is the stopping potential. Vs is the stopping potential, and in this EVS is equal to hc by lambda minus phi naught, we are substituting the values. So, EVS is equal to hc means you can write in terms of nanometers, you can write 1240 electron volt nanometer, you can write, divided by, this is what 200 nanometer, okay, minus, phi naught is 5.01, okay, and here nanometer will get cancelled, and this one will be like this, that is 6.2. So, if you do this division, you will get 6.2 electron volt minus 5.01, right. So, 5.01 is also available in electron volt, that is why no problem, you can subtract. That will give us 1.2 electron volt, 1.2 electron volt, okay. Observe carefully, EVS is equal to 1.2 EV, no. So, EE will get cancelled, no. Then what about VS? VS is equal to 1.2 electron volt. VS is equal to 1.2 VS is equal to 1.2 volt, not electron volt, because electron volt is the unit of energy, not potential. This is what potential, right. So, for stopping potential here, the answer will be 1.2 volt. And from the idea of stopping potential, it is negative potential of collector plates, right. That is why while representing, you have to write like this. That is what the potential difference that must be applied. The potential difference that must be applied to stop photoelectrons. The potential difference that must be applied to stop photoelectrons is equal to minus 1.2 volt. Minus 1.2 volt. Okay. The potential difference that must be applied to stop photoelectrons is equal to minus 1.2 volt. Okay, right. Next, see here, next question, that is what 25th question. See here. So, we completed 24th question. Now, we are going to discuss 25th question. When monochromatic radiation of intensity, right, when monochromatic radiation of intensity I falls on a metal surface, falls on a metal surface. See here, when monochromatic radiation of intensity I falls on a metal surface, comma, the number of photoelectrons and their maximum kinetic energy are n and t respectively, full stop. If the intensity of radiation is too high, so what does it mean? If the intensity of radiation is doubled, if the intensity of radiation is too high, comma, the number of emitted electrons and their maximum kinetic energy are respectively, right? So the answer is, okay, it's simple, it is 2n and t, okay. So n is the, here n is indicating the number of photoelectrons and t is indicating the maximum kinetic energy, right? Just the usual notations he has given, okay, right. Now how this will be 2n and this will be t, that we have to discuss, okay. See here, the relation, that is what number of photoelectrons ejected is directly proportional to the intensity of incident light, that is one. And another one is, maximum kinetic energy is independent of intensity of light, but depends upon the frequency of light, right? So based on these two relations, we can answer to this question. Here, because of depending the number of photoelectrons emitted on the intensity is doubled, no? And moreover, the number of photoelectrons emitted is directly proportional to the intensity of light. So that when the intensity of light is doubled, the number of photoelectrons emitted also doubled. Next, kinetic energy, the maximum kinetic energy of photoelectrons independent of intensity, but depending upon frequency of light. Here is no discussion about frequency of light, right? So frequency of light, we can take it as no change, but there is intensity will be doubled. So when intensity will be doubled, because of having no relation to the maximum kinetic energy of photoelectrons emitted, T value will not change, T will be like that only, so T will be T only. So that's why when intensity doubled, the number of photoelectrons emitted will become doubled, that is 2n, and there is no change in the maximum kinetic energy of photoelectrons emitted, that is what T. Next question, 26th. Photoelectric emission occurs only when the incident light has more than a certain minimum frequency. This is like a definition of threshold frequency. Okay. Even you can check it, that is what practically. Why? Because what is Einstein's photoelectric equation? That is what K maximum is equal to h nu minus h nu naught. That is what Einstein's photoelectric equation. Since K maximum is positive, energy is a scalar quantity. Since K maximum is positive, photoelectric emission occurs only when h nu is greater than h nu naught. When h nu is greater than h nu naught, then what about the relation between nu and nu naught? The relation between nu and nu naught is like nu is greater than nu naught, right? So nu naught is the minimum frequency, that is what threshold frequency. So when the frequency of incident light is greater than a certain minimum frequency, then only photoelectric emission took place. Photoelectric emission took place, then only it happens that phenomena is going to, because the phenomena becomes so possible. Okay, right. That's why here the nu is greater than nu naught. No, that nu naught is called as threshold frequency. So here he is talking about that one only. Photoelectric emission occurs only when the incident light has more than a certain minimum frequency. More than a certain minimum frequency. Okay, right. Next, 27th question. See here. See this. Light of two different frequencies. Light of two different frequencies whose photons have. Light of two different frequencies whose photons have energies 1 electron volt and 2.5 electron volt respectively. Illuminate a metallic surface whose work function is 0.5 electron volt successively. Full stop. Ratio of maximum speeds of emitted electrons will be. Ratio of maximum speeds of emitted electrons will be dash. Okay, right. See here. Light of two different frequencies whose photons have energies 1 electron volt and 2.5 electron volt respectively. Illuminate a metallic surface whose work function is 0.5 electron volt successively. Full stop. Ratio of maximum speeds of emitted electrons will be, so that we have to find, will be dash. Okay, okay. And in this question, if you observe carefully, what they have given, they have given energy of the photons, right? Two different frequencies, and the energies of respective photons will be 1 electron volt and 2.5 electron volt respectively, right? Illuminate a metallic surface whose work function is 0.5 electron volt success. So metal is only one, two different frequencies are there, and because of two different that is what photons means, two different incident lights, that is what energy will be different. So in one case it is 1 electron volt, in another case it is 2.5 electron volt, right? So finally he is asking to find ratio of maximum speed of emitted electrons will be, right? So generally first we have to write the given values. Here what are the given values? Work function is 0.5 electron volt. Work function is 0.5 electron, that is the given value, right? They are also given energies of the photons, that will substitute directly in the respective equation. Next, according to Einstein's photoelectric equation, K maximum is equal to E minus phi naught. Okay, here K maximum 1 is equal to, so in case of this, what is, it is 1 electron volt minus, it is what, phi naught is 0.5 electron volt, that is equal to 0.5 electron volt. K maximum 1 is equal to 0.5 electron volt. It is like equation number 1. Next, K maximum 2 is equal to, right? Here it is 2.5 electron volt minus 0.5 electron volt, that is equal to 2 electron volt. It is equation number 2. Okay, and divide 1 by 2, we will get, see, K maximum 1 by K maximum 2 is equal to 0.5 by 2, that will be 1 by 4, right? So when K maximum 1 means, half mv square formula, right? So here it is half m into v maximum 1 square, and here it is half m into v maximum 2 square, right? So it is v maximum 1, it is v maximum 2, right? 2 square. So that what will happen, half m will get cancelled. Finally v maximum 1 by v maximum 2, v maximum 1 by v maximum 2 is equal to 1 by square root of 4, 1 by square root of 4, that is equal to 1 by 2, that is equal to 1 by 2. Okay, right? V maximum 1 by v maximum 2, that is 1 by 2, right? So whatever he is asking, that we found, that is the ratio of maximum speeds of emitted electrons will be 1 by 2 or 1:2. Okay, right. So in this class we completed 5 problems, right? 23, 24, 25, 26 and 27. Okay, so in our next class we will start with the next continuation problem, that is problem number 28. Okay ma, right. Thank you.